Welcome back. In the previous lecture, we had talked about Cauchy theorems and we had stopped by proving that every holomorphic function is infinitely differentiable. We will pursue from there in this lecture. So we are going to go a step further and we are actually going to say that every holomorphic function which is infinitely differentiable is an actually an analytic function. So let's start with that result. So if omega is an open subset of the complex plane and if f is a function from omega to c, then f is holomorphic at z0 if and only if it has a power series representation in a neighborhood of z0. This basically means that f is analytic, right? And so this power series converges to f uh, for all z in that neighborhood of z0, which is called the domain of convergence or disk of convergence, and that convergence is uniform. Okay. So let's prove the result. Let's prove the converse statement, that is given that f admits a power series form in a neighborhood of z0 about power series about z0 in a neighborhood of z0, then f is holomorphic at z0. So if f admits the power series, it is simple. One can just by term differentiation, one can notice that the derivative of f, so the kth derivative of f evaluated at z0 will be precisely the coefficient ak times k factorial. So this k factorial is coming after differentiating z minus z0 k times. So you'll have k minus 1 and so on, and then when you plug in z0, the rest of the terms become 0. So only the constant term remains, and that is this term. So if f admits power series, then this is then you have fk, which basically means that f is holomorphic, right? This is true for actually every k. Conversely, if f is holomorphic at the point z0, then choose a neighborhood of z0, that is choose a ball, right? So choose a ball of radius. The radius is like this. So you see you are in omega, z0 is a complex number in omega. So you take a curve, any curve that goes around z0, okay, any counterclockwise simple loop in omega enclosing z0, okay, take any curve gamma. So the z0 is in the interior of gamma. So and then you look at the distance between z0 and gamma, okay, which is infimum of the distances from z0 to all the points on gamma, right? So look at the distance from z0 to gamma. Take a radius smaller than that, okay, and then draw a ball of that radius. Call that as the end z0, the neighborhood at z0. So that neighborhood is actually sitting in the interior. It's actually sitting inside the uh, region enclosed by this curve gamma, okay, this loop gamma. So what is that you know with this choice of nz0 is that for all element in that uh, neighborhood and for any element on the curve gamma, the distance of z from z0, because z is in that neighborhood, so the distance from z0, which you know is less than this distance from z0 to gamma, and since W is on gamma, gamma minus gamma naught, it should be bigger. Because that is how you chose your chose this neighborhood. The radius was chosen such that this was happening. Okay, so you have this property, which means that if you start with the Cauchy integral formula for any point z inside the curve gamma, you have a Cauchy integral formula which is given by f of z is nothing but 1 over 2 pi f of w minus z. Right, that's the Cauchy integral formula, w minus z. What we have done here is, in the w minus z in the denominator, you add and subtract z naught. Okay, so w minus z naught plus z naught minus z. So this plus z naught minus z is what we have here as minus z naught, and then you, so this quantity, if you so this w minus z naught will go to the numerator, will get cancelled with this w minus z naught, so you multiplied and divided by w minus z naught. So whatever you had here, w minus z, can be written in this form, where this quantity is 1 over 1 minus something, and this something is such that modulus of that is less than 1. That is how why we chose this. So this is 1 over 1 minus some r or something which is mod of that is less than 1. So you have this geometric series, right, expansion. So from using that fact, we know that this is the limit of this geometric progression, right? Sum of this geometric progressions, and this is less than 1. So the limit of this is 1 minus 1 over 1, 1 over 1 minus r, if you think of this as r power k. So this is by the geometric progression, so geometric series. So now from here you bring out terms like this. So this integral is over w. You see the only w term in the series is this. So you interchange the integral and series. So you have summation z minus z naught power k, which is coming from here, and this f w, and this w minus z naught, this w minus z naught power k becomes w minus k plus 1. And this, if you remember what we had done in the previous lecture, is precisely the derivative at z naught over k. This is something which we showed when we had shown that holomorphic functions are infinitely differentiable. This is the formula that we got. So this 1 over 2 pi I integral over this quantity is fk naught over k factorial. So this is your ak. Okay, if you take this as your ak, you have the power series for fz. So this power series is valid in this neighborhood. You have obtained a neighborhood where this is valid. So this is called the Taylor series, right? This is something which you have come across in the real situation as well, in real analysis as well, right? So what you may have here, I mean, I have not given you the full detailed proof, right? I mean, basically, you have this Taylor series, and this will converge to this F uniformly, but all the details are there because we started with this equality and so on. We just use this convergence that we had here, and that convergence takes care of everything else. Okay, so now that we have done Taylor series expansion, let's see. So this is something very special for holomorphic function. Like in the real situation, this is not true. In the real situation, you have infinite differentiable function which we denote as C infinity functions. Then you have the class of analytic functions, These analytic functions are actually a subclass of C infinity functions, in fact a proper subclass of C infinity functions, which means there are C infinity functions which are not analytic. So which means there are infinitely differentiable functions which are not analytic, whereas here we have already seen holomorphic function is infinitely differentiable and every holomorphic function is also analytic. So every infinite differentiability is also giving you analytic, and all this is a property of holomorphic function. So in a sense, you can think of the complex function theory, complex derivative of complex functions, as a kind of understanding actually real analytic functions. So if you have a appropriate extensions from the real analytic to complex analytic, so this kind of has this nice property, and the reason why it behaves nicely is also the property which I've seen before, that every holomorphic function is actually an harmonic function, which is a solution of a differential equation. So you have these nice properties that you have here. So it kind of so look so in a sense, studying complex functions is actually studying some restricted class of functions, whereas real functions have kind of more possibilities. As an example, I mean, just to say in the real case, you must have come across this before. I remember even someone made a presentation and that time probably gave this example. But you please try to give a proof of all this thing that I'm going to say about this example. I'm just only going to state the facts and sketch, but you complete the proof. So this f is a real valued function, which is 0 in the negative real axis, and in the positive real axis is exponential of minus 1 over x. See, this exponential of 1 over x function has a very different behavior at origin, because when let's take say 1 over x or minus 1 over x, it doesn't matter which one. So if you take exponential of minus 1 over x, if you take this function, you see that when x is going to infinity, say, so when x is going to say plus infinity, when x is going to plus infinity, then this term is going to 0, right, which means this is going to 1. So as x goes to infinity, this function goes to 1. Similarly, when x goes to minus infinity, again this function goes to 1. Okay, so asymptotically it kind of goes to 1 at when x goes to 0, because at x equal to 0 this is infinity not defined. So if you can actually notice that when x tends to 0, it takes two different values depending on whether you are coming from the positive side or negative side. So if you come when x is positive, if you come from the positive side, minus 1 over x as x goes to 0 is actually going to minus infinity. So exponential of minus infinity tends to 0. So as x goes to 0 from the positive side, this function goes to 0, and it goes to 0 in a very smooth way, right? You know how exponential touches 0 when in the negative real axis, right? It kind of asymptotically goes to 0, and when x is coming from the negative real axis and x goes to 0, then this is again when yeah, when from negative axis, if it is going to go to 0, so this is going to go to minus infinity, sorry, plus infinity, and this is going to blow up infinity. Okay, so that's the property of this function. So what we have done here is that the case where it goes to infinity, that part we have made it 0, right? So on that side, on the positive side, we said this goes to, as x goes to 0, this actually goes to 0, right? Because x goes to 0, this goes to minus infinity, so exponential of that goes to 0. So it goes to 0 in a very nice way. So it actually goes smoothly and touches 0. In the sense, what we say is that this function is infinitely differentiable. You can verify that. Okay, you can actually write down the derivative of this exponential minus 1 over s. So this is actually infinite. So the real trouble is only at the gluing point, that is the 0 point. Everywhere else it's infinitely differentiable is obvious. Okay, when x is strictly greater than 0, it's obvious because it's an exponential function. We actually have a Taylor series expansion of that which actually converges this function, and similarly for x strictly less than 0, it's a constant function 0. So there is no issue. This is infinite differentiable. So the infinite differentiability has to be checked only when x is equal to 0. Okay, and that one can do. You can actually compute that the derivative of. So when you actually compute the derivative at 0, you need the previous derivative at the point h, which is the derivative of this. And if you differentiate this, you can actually see that the derivative of this will be some polynomial in if you're looking at the kth derivative, some kth derivative polynomial in 1 over h multiplied by exponential of minus 1 over x, and you can do an estimate to actually show that then the numerator will go to 0 faster than this. Okay, so that way you can actually show that this function is infinitely differentiable even at 0. So it's actually a C infinity function, whereas this function is not analytic. That is, you cannot have a power series form of this which converges to this function. And that is, if you see, the problem is only at 0. At x strictly greater than 0, it is, yeah, it is. You have an expansion, power series expansion. This is again 0 for x strictly less than 0. But when x is equal to 0, so f fails to be analytic at x equal to 0. Okay, about 0. So if you write down the Taylor series expansion of that function, you will get this, and you will see that it converges to the 0 function for all x in R. Because you just proved here that the derivative of f at 0 is always 0. So if you use that information, write down the Taylor series about x equal to 0, these coefficients are 0 for any real x. This is going to converge to this power series is going to converge to the 0 function. Whereas whenever x is positive, you know that this is not the case. Right? Whenever x is positive, you know that it is exponential of something else, which is not a 0 function. So the Taylor series does not converge at x equal to 0, right, to the function. I mean, it converges to 0, it converges to something else. It doesn't converge to the to the given function f. Okay? So in any neighborhood of x equal to 0, right? For the positive side, you see that you have 0 here, whereas when x is greater than 0, this is actually exponential of minus 1 over x. That's not the case. So this is not analytic. So if it's not analytic at 0, so this is an example in the real situation. This is not happening in the complex variable. That's what we wanted to highlight. Right? So in the complex variable, holomorphic functions are infinitely different. Holomorphic functions are infinitely differentiable, and hence are also analytic functions. Okay. Now that we are in the analytic function and we have written down the Taylor series form, as you see here, we have written down the Taylor series form. We can talk of zeros of function. For instance, if the leading term, the first term a0, if that a0 is 0, then z0 is actually z0 is a 0 of this function, right? So looking at Taylor series, one can say many things about the zeros of this function, of this holomorphic function. So what are zeros of holomorphic function? So we say a point z0 in C is said to be of so is said to be 0 of order m if f evaluated at z0 is 0, and it's of order m if f evaluated at all the derivatives of f evaluated at z0 is also 0 up to m minus 1. So the 0 corresponds to the f being so j equal to 0 corresponds to f vanishing at z0, and starting from that up to m minus 1 derivative if it vanishes, and m plus 1 at m it does not vanish. So for m it is necessarily not equal to 0. I should have actually said that strictly, right? So this is it's 0 up to m minus 1, and fm of z0 is non-zero. Then you say it's of order m, and you say it's a simple 0 if m is equal to 1. So if you imagine this in the Taylor series expansion, any non-zero holomorphic function, for any non-zero holomorphic function, at least one coefficient of Taylor series is non-zero. Okay, because suppose the holomorphic function is suppose it's a zero holomorphic function, that means all the coefficients of the Taylor series should be zero, right? The power series content should be zero for the function to be zero. So if it's a non-zero function, then at least one coefficient of the Taylor series is non-zero. So coefficients are actually given by this over some factorial, right? So it basically depends on only this. So at least one of them is non-zero. So let's choose the first one that is non-zero, right? The first non-zero coefficient in the Taylor series. And when I say first, in that order that we have written, starting from zero order term, first order term, and so on. Okay. So in that, the first non-zero coefficient, right? If that is m derivative, if the first non-zero coefficient is m derivative, then z0, and this Taylor series is about z0, around z0. Right? So it's expanded around z0. So then, if this is the first non-zero coefficient, then that z0 is a 0 of order n. So if you use the Taylor series again in a neighborhood of z0, wherever you have the convergence of the Taylor series to the given function, then because if f is holomorphic and it has a 0 of order m, right? If it has a 0 of order m, then f can be written as product of two functions like this, where so z0 is a 0 of order m, so you take z minus z0 power m, whatever remains will actually be this series, and g of z0 is not equal to 0, right? You can see that because when you put z equal to z0, the k equal to 0 situation is the constant coefficient, and on when k equal to 0, fm of z0 is non-zero because z0 is of order m. So you can actually decompose the given function. If it has a 0 of order m, f can be written like this, where g is non-zero at z, or that 0 of f, that is f, which is z0. And this is the power series expansion of g, and this has the same domain of convergence or disk of convergence as f. Okay, so this is a property. So once you have the Taylor series, you observe this property one about zeros of the function and so on. Now the thing is, how many zeros does an analytic function have? That's a very, suppose we ask this question. If you recall our first lecture when we did fundamental theorem of calculus, we said that all complex polynomials have exactly as many zeros as its degree, right? And when and that that so as many zeros, when we say as many zeros, it's also include multiplicity. When we said multiplicity is what this order of the zero is. Zero of if there are so order of the zero is basically the multiplicity of 0. So we have seen this, that every complex polynomial has exactly as many zeros as its degree. So for a polynomial, the degree is finite. So the number of zeros are finite. And now we have seen, after all this theory that we have developed later, is that the complex polynomials are actually analytic functions, right? Where the Taylor series truncates after some point, right? So it's not an infinite series; it's a finite series. The Taylor series truncates after a finite number of terms. So roughly, one can imagine the analytic functions which has a Taylor series power series form as polynomial of infinite degree if it is going for infinite number of terms. If it truncates after finite number of terms, it's a finite degree. Right? That is right. So Taylor series can be thought of as some kind of infinite degree polynomial. Right? So we can ask this question. So what about the number of zeros? So is it that since the finite degree polynomials had finite number of zeros, so infinite degree polynomials, do they have infinite number of zeros always? Can we extend this statement of fundamental theorem of calculus to say that you have infinite number of zeros? And when we say infinite here, it's a countable infinite because it's a series, right? So it's a countable infinite. So do we actually have at most countable zeros for analytic function? Uh, that statement is true. At most countable function, countable zeros is true, which we'll see at the end of this lecture. But it is not true that it always has as many exactly as many zeros and so on. For instance, something like in contrast to polynomials, look at these. If you take a non-zero, non-constant analytic function, then there are examples where they don't have any zeros. They don't have any and complex zero. Right? There is no complex root to and these to some non-zero non-constant analytic function, which is different from what fundamental theorem of so sorry I said FTC, it should be FTA. It's fundamental theorem of algebra. That's what I mean here. I'm sorry for this typo here. It's fundamental theorem of algebra, okay, not fundamental theorem of calculus. So that statement says that every non-zero, non-constant polynomial of degree k has at least one root and so on. So you can actually kindly conclude that has exactly as many k's as many zeros as its degree. But that's not the case. For instance, examples like something like 1 over z, exponential over z, like exponential over so exponential of z does not have any zero at all, and it's a holomorphic function in the entire C, right? And it has no zeros. Okay, it has no zeros. Uh, okay. Similarly, you take 1 over z, exponential 1 over z. 1 over z is um, again a analytic function, and this will also have no zeros. In fact, you have a singularity of this, so at z equal to 0, this is actually undefined and so on. Similarly, you also have a singularity for this at z equal to 0, again this is undefined, and this doesn't have any zero at all. So you have analytic functions which has no zeros. But there are situations like sine z, which has countably infinite zeros. You can actually use the formula that sine z is exponential of iz minus exponential of minus iz over 2i and so on, right? So we use that formula. So any zero of that should be actually zero of this function, and those zeros are precisely k pi for all integer k. So you have countably infinite zeros. You have as many zeros as integers. This is another example where you have just taken sine 1 over z. Again, like the previous cases here, when z is equal to 0, you have a singularity here. It's not defined at z equal to 0, but everywhere else, so in the punctured plane, that is c minus 0, in that said this is it's an analytic function, and if you look for the zeros of this, if you use a similar format, you see that the zeros of this should be 1 over k pi, right? This is 1 over k pi, so it's actually, again, you have a countably infinite zeros, and but this 1 over k pi, if you see as k goes to infinity, it actually goes to the zeros of the sign 1 over z actually converges to 0, and on 0 this function is not defined as singularity. So you have a countable collection of zeros, but its limit is and the limit of that it's singular. For instance, you see sine is a continuous function. So if this is a sequence converging to 0, then then if it was a continuous function, then the sine of this should converge to sine of the limit of this. Sine of this is 0, so the limit of that should be 0, but the limit is actually singularity. So this is something which again we will see again later as a property of holomorphic functions. Okay. A last example is something like this, where you have sine hyperbolic function, use similar expansion. Now you will see that you have again countably infinite zeros, but now the zeros are all imaginary zeros, I k pi, all lie on the imaginary line. Here the zeros were lying on the real line, and here the zeros lying between 0 and 1 in a finite interval. All the zeros were lying here, whereas for this again the zeros are lying on the imaginary axis, imaginary line. So you have such observations about zeros. So let's understand uh, about the zeros of holomorphic function. So the first property is that if the holomorphic function is non-zero, then the zeros of that holomorphic function are isolated. That means whenever the function becomes 0 at a point, then there is a neighborhood around the point where the function is non-zero. So it's an isolated 0. There is no nearby 0. When we say nearby, that means there is a neighborhood in which there is no other 0. You can isolate that 0, 0 z naught. That's what the statement is. That every non-zero holomorphic function has, see, if you have a 0 function, of course it's a 0 function, it's 0 everywhere. Okay, so that has infinite number of zeros. That's a constant function, right? Constant 0, constant function 0. If you have a non-zero holomorphic function, then its zeros or roots of that function, you don't call roots, you only use the term roots for polynomials, so that's why I'm using the word zeros. So the zero of the function is isolated, it's an isolated zero. So let's look at a proof of this. So since f is a non-zero function, uh, without loss of generality, we can assume that the zero, which is the z naught, which is 0 of f, is of order m, which is finite. It's not infinite order. Why? Because if f is non-zero, that means one of the coefficients in the Taylor series has to be non-zero, right? So if you know, choose the first non-zero coefficient and choose m, that m should give you that the z naught is of order m. M could be 1 as well. Okay, so so z naught is of order m, and we have already observed that if we have a 0 of order m, this f can be decomposed as this, where g is another holomorphic function, right? Because it had a Taylor series expansion, right? G had also had a Taylor series expansion. It's another analytic function, holomorphic function, but with the property that g of z naught is non-zero for that. Okay, so g of z naught is non-zero. Now, if g of z naught is non-zero, g is a continuous function because it's an analytic function. It's a continuous function, so, and a continuous function is non-zero at a point which means that there is a neighborhood around that point in which the function is non-zero. So since g is non-zero at z0, there is a neighborhood uh, of z0 in which in this entire neighborhood g is non-zero. Okay, and in that neighborhood g is non-zero, and in that neighborhood z minus z0 is also non. So except z0 we have already said it is 0. So if so every other point in this neighborhood except z0, z minus z0 is non-zero, because this is 0 only when z is equal to z0. So for every other z0 in this neighborhood, so the z minus z0 is non-zero, gz0 is gz is also non-zero for all the z in the neighborhood, which means fz is non-zero in this entire neighborhood, this epsilon neighborhood here. So fz is non-zero in this neighborhood, which means that we have shown that z0 is a 0. There is a neighborhood where fz is non-zero, which means this 0 is isolated. Okay. Okay. Now let's prove another theorem. It's kind of converse to previous statement, right? Previous statement we said that if the function is non-zero, the 0 has to be isolated. Okay, and here we are saying now, if there is a sequence of zeros and all these zeros converge to some point in the domain of f. Okay, so that means there is a limit of this sequence of zeros which is sitting in the domain of f. If that happens, then f has to be necessarily 0. Okay, so you start with the holomorphic function. What we have said is like converse to the previous statement. Earlier we said if something is non-zero, then the 0 has to be isolated. What is the converse of that? If the 0 is isolated, the function has to be non-zero. That's the converse statement of that. So if we need to prove this, that is isolated 0 implies non-zero function, right? So if you need to prove this statement is equivalent to saying, so P implies Q is not Q implying not P. So this statement is equal to saying that a non-zero function implies a accumulation point and so on. So that's what we are saying here. So you have a sequence of zeros which converge in the domain of f. Okay, so that is z0. Then if that happens, then f has to be 0, which means that the 0 set of f, so for a non-zero function, the 0 set of f cannot have an accumulation point. So zeros cannot be accumulated. Zeros always has to be isolated. Okay. So how do you prove this? You start with this set E, which is all the elements in omega, such that there is a sequence Zn, right? Non-trivial sequence, I mean, which means that we don't take the sequence when a constant sequence Zn equal to Z. Suppose I pick a Z. The constant sequence is also a sequence. I am not talking about that kind of a sequence. I am saying suppose so all the Z in omega, which are the accumulation points of zeros of f. That's what it's saying here, right? So this is saying that there exists a sequence. Now this sequence is actually from the 0 set of f. So there is a sequence in the 0 set of f such that z is the limit of that. So this E is nothing but the set of all accumulation points of the 0 set of f, right? Of the 0 set of f in omega. Okay. So by definition, you see that this E is not empty, right? Because Z naught belongs to E, because Z naught has a non-trivial sequence Zn, which converges to Z0, and f of Zn is 0. So E is not empty because Z0 belongs to E. Secondly, you also observe this, that for every point by the continuity of f, since E is defined as the accumulation points of zeros, f should vanish on every element of E as well. So f of z is 0 for every element of E. Okay, this is on the accumulation set also, the f vanishes due to the continuity of f. Second, the third thing is that E is closed in omega. I leave it as an exercise, it's easy to check immediately. Okay, this just points at topology closeness. So you just have to show that E is closed. That means if you take any sequence of points from E, and if it converges, then the limit is also in E. Okay. So E is closed. So now what we are going to claim is that E is also open. So E is basically a non-empty, both open and closed set, right? And omega is a open connected set. So E is a open and closed subset of the connected set omega, which means it has to be either empty or the full set. We have already verified that E is non-empty. So if we show that E is open, then E has to be the full set, which is omega. Okay, so let's see whether E is open. So we claim E is open. So pick any point W in E. So to open, what we need to do, you pick any point in E. We need to show there is a neighborhood uh, in E which contains a neighborhood around W which is contained in E. Right? We have to get an open set, right? Open point, open ball. Right? To show that it's open, we have to show there's an interior point. W is an interior point. But W belongs to E, so choose that E. But this W, because E is contained in omega, it's also W also belongs to omega. But omega is an open set, so W is an interior point of open set. So there is a ball in omega containing W. Okay, so there is an open ball containing W in omega. Now this f of W is 0 because W is chosen from E, and we have already shown that f vanishes on every point of E. So f of W should be 0. Now since f of W is 0, suppose that f is non-zero in B. We need to show that f is 0, right? Suppose f is non-zero in B, in this ball B. Okay. B is a ball which is containing W, and W is a 0 of f. So suppose f is non-zero in B, except of course at W. So it's non-zero in B. Then W is an isolated singular. W is an isolated 0. So when we say non-zero, it's non-zero in every point of B, which means that W is an isolated 0 of f. But f is given to be an holomorphic function, right? And which means that f has to have isolated 0. So suppose we assume that this is non-zero, then W is an isolated 0 of f, but that is a contradiction to the fact that W belongs to E, right? Why? Because E was precisely the accumulation set of the zeros of E. So once W belongs to E, there is a sequence in omega of zeros of f such that it converges to W, which means that any neighborhood, any open world that you take, it should be contained so infinitely many terms from the sequence should be contained in that world. Okay. So the fact that W is an isolated 0 of f, because f is holomorphic, so the 0 has to be isolated. Contradicting, so a non-zero holomorphic function is isolated thing contradicts the fact that W is in E, which means our assumption that F is non-zero in B is false, right? Which means F has to be uniformly zero in B. Okay, so if F is uniformly zero in B, we have actually shown that that this this E is open. I mean, E is open. Why? Because you chose a W in E, and you obtained an open ball, and you have shown that by showing that F is zero and open ball, you have shown that this B is actually in E as well. So it's a open ball sitting in E. So hence E is open. So as I said, if it's an open and closed non-empty subset of a connected subset, so E has to be the full set, which means that uh, omega is the set of all accumulation points of which means that F vanishes on the entire set omega. Okay, I hope this works. I mean, yeah, I know. I mean, uh, I kind of went very slow here, but hopefully you understood what I mean the point that I was trying to make. Okay, so let's see you in the next lecture. Bye.